Welcome to Machine Learning First Steps, presented to you by Samer. Today our topic is linear regression. So what we did so far is that we learned how to set up our project environment using virtual environments and using an IDE in order to store coding for our machine learning projects. We also learned how to code using Python. We used some simple examples that will help us establish our basic knowledge of Python, which we're gonna build upon in our next tutorials. So what are we gonna do in this tutorial? We are going to understand the basic theory behind linear regression, which happens to be the very basic problem of, or the basic foundation of machine learning. We will get ready to implement linear regression on a real-life situation in our next tutorial session by understanding the basic concept of linear regression and then trying to use Python in order to implement linear regression on a real-life problem. So let's go. So right now we'll start with some theoretical background about the earliest machine learning problem we have. So imagine we have a problem like predicting house prices, which happens to be one of the most famous first examples of any machine learning tutorial or course. So imagine we have something like this. A plot that indicates the relationship between house price in dollars and its size, for example, which happens to be in meters squared. So if you try to plot some real-life examples, you'll get something like this. For example, we got a house that lies somewhere here. So based on its size and its price, we just plot this point here. And we got another example, for example, here. We got some third example here, and maybe some fourth example, and so on and so forth. So eventually we'll get something like this, but we need a lot more points to be able to predict what the relationship would look like. But judging from these points we have so far, we can predict that the relationship between price and size is almost linear one. And by visual inspection, we can pick some straight line to represent this relationship based on our own estimation. But we got no mathematical proof for this right now, and we don't have like a solid basis for this claim. This is known as a regression problem, and this linear regression method we are going to present right now was adopted by a scientist called Gauss. This is an example of a supervised learning problem, and the reason why we call it supervised is because we have some training examples that we can learn from, or try to create a relationship between two variables based on some training examples and based on our own intuition. So we do have some examples in order to support our claim. So let's just pick some variables or some notations in order to better describe our problem variables. So first we have the number of training examples, like the 6 points we have right here. So we will denote that by m, which is going to represent the training examples. And we also have some inputs, which happens to be the size of the house right now. So we have inputs, and we're gonna denote that by x, which is the global symbol for any input of any equation or any function. So we're gonna call that input. And in machine learning, we always refer to the input using another term, which is called features. Also, we have the output variable, which is obviously going to be y, and this is the output, sometimes called a target variable. So in order to solve this problem, we need to create a linear relationship here, or we need to estimate a linear function that could better, or that could best represent the exact relationship between price and size, it is almost impossible to get a linear relationship that could accommodate all of these examples simultaneously. So, our best hope is to get a linear relationship that could be as close as possible to the real life situation. So, this gave rise to machine learning because here we're trying to solve the problem not with an exact solution or an exact analytical solution using linear algebra, for example. Here we're trying to get some best estimate, but we can't find an analytical exact solution. So our problem can be represented using the following graph. Let's just say that we have some input, which is the size of a house, and we want to develop or we want to create some function, let's call it f, for example, which could map estimated price to size. And in order to do that, we need first to create some objective function, j. And what this objective function does is that it represents some parameter or some value or some entity that, if optimized, could help us create the optimal function f in order to map size to the estimated price, or map the estimated price to size. So we first need to create this function, j, in order to get the optimal function f. And in order to create this j, we have to rely on our intuition and logic. But also, once we get this j, which is the objective function, we need to optimize it in order to reach the best possible solution. So we gotta have something called a learning algorithm. In order to optimize this function j, which would lead us to find the best parameters we could have for this function f. And in order to do that, we have to feed our training examples to this learning algorithm in order to work on optimizing j, in order to get the best possible f, and then we can use f to predict estimated price based on the house size. So first of all, how do we represent the function f here, which we would call hypothesis? Some people do that. So in our simple problem right here, we might have some intuition about the exact shape of this function or how it looks like. So in this particular case, we will consider that this function is a linear function. So I'm just going to call this f of x is equal to mx plus b, for example, which is the general standard format for any linear function. So we got the slope m and we got the offset b. But in machine learning, we're going to use different notation for this. So instead of m and b, we're just going to use theta 1 and this to be theta node, where basically this index here, or the subscript, represents the power of the variable x. And because we have x power 0 here, we can just say theta 0. And this is x power 1, so we got theta 1. So we can imagine that this function should be something like this. So as opposed to linear algebra, where we usually have some input and try to produce an output while having theta node and theta 1 as constants, here we have a series of x's, or a series of inputs, or a series of features, and the corresponding series of outputs, and we're trying to estimate the values of theta node and theta 1. So it is quite the opposite, and this is why this problem is called linear regression instead of normal linear algebra, which relies on analytical solutions. So there are many ways to draw this function based on the values of theta node and theta 1. For example, we might have something like this. For example, we might have theta node equal to 0 and theta 1 equals to 1, for example. So the function f of x is equal to x, and we get something like that. Or we might get something like fx is equal to theta node, which means fx is equal to a constant, and it would look something like that, with this being theta node, for example. So by manipulating these two parameters, we get different shapes. So how to get the optimal parameters? This is the question that we should ask ourselves. And this would lead us to the objective function part. What kind of objective function do we need to optimize in order to reach the best optimal solution? So returning to the graph here, we find a number of training examples here. So based on visual inspection, we won't pick a linear relationship that looks like this, for example, because this seems very far away from the examples that we have, and it wouldn't be able to predict the values accurately. So instead, we might draw something like this. And our criteria for that was that we were trying to minimize the error between these points and the curve that we're trying to draw. So we got some distances here, like this one, for example, and this one, and this little distance here, and this little distance, and this one, and this one. And what we're trying to do is to minimize these distances. So if you're going to pick one of these distances, so we can represent the error or this distance using the following. Our error of prediction relies on the error in predicting y, so we can minimize this distance by saying the error is equal to the, for example, the predicted value, which is f of x, minus the actual value, which is y. So this is one way of presenting this distance. And as a matter of fact, we can pick this to be our loss function. And loss function here refers to the error for a single example. So if we try to optimize this, our best approach is to minimize this function as much as we can. But because our function here is boundless, which means that if we try to minimize it, we'll just get to negative infinity. That means there is no bottom for this function. And we needed to have a bottom so that we can try to reach that bottom. And once we are close enough, we can say that our function is optimal. In order to do that, we get the square of this error, or the absolute value. But here we're going to pick the square because a squared function always has the minimum value 0. So what I'm going to do here is I'm going to represent this loss function or error. Let's call it L instead of E. And this loss here is going to be half fx minus y squared. So this is good. So right now we have something called a convex function, and a convex function is a function that I could minimize the right way, basically. Without getting into the mathematics right now, we'll get to that later, but we'll just say that our function is now convex and it has a bottom or a global minimum that I could reach in order to solve my problem properly. But the problem is we got so many distances here, so we got so many errors between the actual y and the prediction. So we have to take in mind, or we have to consider all of these individual distances at the same time. One logical approach would be to get the average of all of these distances, or all of these errors, or all of these losses, and try to minimize that average. So in order to do that, we will define a function called j, which is our objective function. So what j is going to be the average value of all of these individual losses. So that means we'll get the summation of all of these losses. For example, let's put the subscript I here. which means loss, for example, I. And we're going to take the sum of all of these, starting with I is equal to 1 and up to m, which is the total number of training examples. And we're going to take the average by dividing over the number of training examples, which is m. And this means we can write this objective function as follows. We can write it like this. So j will be equal to 1 over 2m multiplied by the summation starting from I is equal to 1 and up to I is equal to m of the individual squares of errors. So we got f of xi here, which is the input of example I, and we've got the exact output yi, and we've got all of this squared. So we managed to get an objective function for this particular problem that would allow us to pick the ideal values for theta node and theta 1 and thus create our hypothesis or optimal function f for prediction. So we can represent j as a function of theta node and theta 1 now. Or we can write it like this. So we need now to pick the values of theta node and theta 1 that are going to minimize this objective function. So now we can summarize what we said so far. So right now we have a hypothesis, and it's a function that we're willing to use to predict housing prices. So this is going to be theta node plus theta 1x, and we've got some parameters here, which are basically theta node and theta 1, the parameters of our linear model, and we've got a cost function, which is j theta node theta 1 is equal to 1 over 2m, summation I is equal to 1, up to m, the hypothesis of xi minus yi all squared. And the goal is to minimize this j function. So we need to pick this theta node and theta 1 that make the value of this function minimum. So how exactly are we going to do that? Here we need to explain a concept or a method called gradient descent. So what we need to do here is to assume that we have some initial parameters, theta node and theta 1, that have been selected randomly. That means I don't really know what the correct values of theta node and theta 1 are, but I'll just start with some random values for theta node and theta 1. And then I'll keep changing theta node and theta 1. For example, let this be the first assumption, then a second iteration, and so on, till I get to theta node and theta 1 that successfully minimize j theta node and theta 1. So in order to do that, we need to explain something regarding optimization of this sort of function. So since our function j is a convex function, so it would look like this, like a parabola basically, because it's a square function, right? And this is the value j, and let's just say that we have some theta node and theta 1 that minimize the function. So this curve is going to be a 3D curve. And in order to represent a 3D model of j, we'll just draw some volume here. Need to make this a bit smaller. Let's just say it will look like this. Let's give it some colors to represent the exterior, and another color to represent the interior. So this is basically our function. And once we start with some value for theta node, for example, and theta 1, let's just say we start somewhere here on the curve. So the probability of us choosing the values of theta node and theta 1 that make this function minimum is very low at the beginning, since we're using a random initialization. So what we need to do is to keep walking till we reach this minimum. So how are we going to do that? Basically, if we have a 2D function like this, or 1D function like this, and let's just call it h, for example, another function. And let's just say that h is a function of some theta here, not theta node, not theta 1, just theta, a random variable. And let's say that h is a convex function, which happens to look like a parabola. Same concept, but just 1D. So let us assume that we start with some random theta here, and we need to reach the theta that makes this function h minimum. How are we going to do that? One idea is to use the concept of the derivative. So what is a derivative? A derivative basically is the slope of the function at some point. So this is considered to be the slope of the function, which is tangent to this function at this particular point. So once this tangent is parallel to the x-axis, or the theta axis here, we can say that we've reached the minimum point. So the derivative is always associated with the concept of minimization. And if we want to reach that point, we can start with an algorithm called gradient descent, which basically states that if we have an initial theta here, so let's call that just theta, and if we happen to subtract the derivative of the function h at this particular point theta, so let's just call this theta initial, for example, or let's just call it theta j, right, where j represents, right, we have another j already, so let's just denote this by k, for example, where k is the iteration number. So basically, if we subtract the value of the derivative of h by theta at this particular theta k from theta k, we can obtain a new theta. So we can just call that theta k plus 1, which is, this is iteration number k, so this is going to be iteration number k plus 1. So basically obtain the new theta starting from the old theta. And this means that if we repeat this operation over and over, we'll eventually reach the point that minimizes the function h. And the reason behind that is, if we happen to be at this particular theta k value here, and we compute the derivative, we will find that the slope or the derivative looks like this. So this slope basically has a positive value. So we can say that it has a large positive value since it's almost parallel to the x-axis. So if we try to subtract that derivative value from theta k, we'll end up moving somewhere here because the value of theta would decrease. So let's just say we'll be at a new theta here, and our new slope at that particular new theta with theta k plus 1 will look like this. We can see that the value of the slope is still positive, but it is kind of reduced with respect to the other slope. We can say that the value of the slope was, reduced significantly due to this kind of motion. And if we plug in the value of the new derivative in this equation to obtain the theta of the new iteration or the current iteration, so we're going to plug the value of the derivative of h by using the point theta k plus 1 and the point also theta k plus 1 in order to get theta k plus 2. And we can see that theta will continue decreasing, but it will not decrease with the same factor as before. It would just be reduced, but less than before. So let's just say the theta will end up somewhere here, for example. And we get a new slope, which is also positive, but with a slightly reduced value. So that means if we plug in that value of the derivative right here into this equation once more, so we get theta k, for example, plus 2 now, plus 2, and we use theta k plus 2, so we'll get theta k plus 3 in this case. We use theta k to the theta k plus 1, and then theta k, I guess this was theta k plus 1. So this is supposed to be theta k plus 2, I guess. So yeah, this is supposed to be 2, and this is supposed to be 1. Right, the numbering doesn't matter. We just understand the concept that we're moving from one iteration to the next. So basically, if we use that value here, that value is supposed to be very small. So the motion here will be very small as well. And eventually, we reach the point at which the slope is equal to 0. And if we keep iterating using this point, there will be no change to the value of theta over the new iterations, because basically we'll use the derivative at this new point, which is theta k plus 2, which happens to be 0, so this factor will be eliminated. And as a result, theta k plus 3 will be equal to theta k plus 2. So that means if you apply gradient descent over and over, we'll eventually reach the minimization point. So this is the concept behind gradient descent. And we can actually use gradient descent even for this 3D shape we have right here, because the derivative or the slope will have two components instead of just one. So what will happen is, if we keep applying that for both theta node, so theta node, or the new theta node, will be equal to the old theta node minus the partial derivative of j by theta node at the old theta node. And the reason why I'm using a partial derivative here, if you don't happen to be so good at calculus, it's okay. The partial derivative has the same concept as the normal derivative, except that we call it partial because here the function is a function of two variables instead of just one. So the derivative has two components, and one of these components is partial j over partial theta node here. So this is why we call it a partial derivative rather than a full derivative. And the same thing goes for theta 1. So theta 1 be equal to the old theta 1 minus the partial derivative of j by theta 1. We got theta 1 here. So eventually, theta node and theta 1 will keep moving in a way so that we'll eventually reach this point we need to reach, which is the minimum point. Because at the minimum point, the values of theta, or the values of the derivatives, will be very small, that very little change occurs to theta node or to the values of theta node and theta 1 over the new iterations. And basically, we can reach that minimum point, which means we've succeeded with our mission to get the optimal theta node and theta 1, which makes our prediction as close as possible to reality. Now we need to generalize the solution to our problem, considering that many problems do not just have one input variable x and might have multiple features. For example, for housing, you might have some input features like not only the size of the house, but how many stories, for example. It might be a multi-story building. Also, it might have a garden, or it might not have a garden. Also, the area is a factor and the council tax is another factor. So there are a lot of factors that control the price of a house, and there are a lot of factors in general that will be associated with any regression problem. So let's just say that our hypothesis will be actually a function of many x's rather than just one x. So we got x1, just x1, x2, up to xn, for example. And that will be equal to theta node plus theta 1, x1, plus theta 2, x2, plus, up to theta n, xn. In order to make this more readable and easier to represent, we'll just represent this in vector form, where we say that there is an input vector of features x, or capital X, which is equal to a vector theta transposed multiplied by this input vector x. So instead of just representing it in a singular format, we're going to use the matrix format for this particular problem. And this allows us to create a more general solution. And in this case, we can apply the same exact concepts that we used before, like, for example, gradient descent. But instead of applying gradient descent just once or twice, we're going to apply it for each parameter theta. So for example, we got theta node will be equal to theta node minus the whole derivative. And the derivative here is considered to be the derivative of the objective function itself. So we need to compute the derivative of j. And this is pretty easy actually, because since it is a squared function, we can do that same way we can do this. For example, let y is equal to half x squared, then the derivative of y is equal to basically x. And we're going to do the same exact thing here. We know that the objective function is 1 over 2m multiplied by the summation of the square of errors. So basically, we're just gonna eliminate the square, and we eliminate the half, or the constant factor half, from the expression in order to obtain something that looks like this. 1 over m summation I is equal to 1 up to m, and we're going to include the error between the prediction at xi minus yi. And we're going to multiply this by some factor here that is a byproduct of the derivative or the derivation of the derivative process itself. For example, if you got an expression that is slightly more complex than the last expression, so let's just say it's y equal to 1 half of 2x squared. So what are we going to do in order to get y dash, or the derivative of y with respect to x? We're going to have the formula which dictates that we're going to subtract 1 from the current power and just let the current power pass on as a constant factor. And this constant factor here is 2. So this will be power 1, which is 2 minus 1. And then we get 2 over 2 here, because 2 will pass on here. And then they'll just eliminate each other. And the last part is to get the derivative of the interior expression of the squared term. So this will be the derivative of 2x, which is 2. So this is why we need to multiply this by this byproduct or external factor that we need to get here. So this factor is going to be actually xi. So basically, yeah, we need just to get this I here. Right. So basically, we got the derivative of j. And we know that fxi is actually a function of theta node and theta 1, and this is where theta node and theta 1 and theta 2 and theta 3 up to theta n would appear. So this function here is actually also a function not just of xi, but of xi, theta node, theta 1 up to theta n. So we're going to substitute with all of these values here within this expression. And at the same time, we need to consider another factor that we're going to add here, and this factor was added by us, called the learning rate, and we're going to denote it by alpha. So this learning rate here controls the speed with which our point moves along the curve. And this allows us to gain some control over the speed of the learning process itself, and hence this parameter is called the learning rate. So it is an artificial parameter that we added just to tune the learning process. And we'll learn how to manipulate it later. And since this parameter doesn't have to do with the formulation process itself, we often call it a hyperparameter. That means a parameter of our own selection, or a parameter that we're actually able to tune ourselves. So we're going to repeat this for each variable theta or element theta of the main vector. So we got theta 1, which is also going to be equal to theta 1, or the old value of theta 1, minus alpha over m, summation I is equal to 1 m fxi minus yi, all multiplied by xi. But we gotta take care of a certain aspect here, that this xi is not actually like the entire vector or the entire input feature vector. This xi here represents the vector xi, so we should have written it as capital X rather than just x. And we need to consider that this factor x here is not a vector, but rather it's just like an element, which is the element associated with this particular theta. So we should have considered the very first element of our vector theta here, since these subscripts should match. And the same thing goes here for this expression. So basically we got yi here and then multiplied by xi of the example number I, but at the same time this has to have the subscript 1 to indicate that we're using the second element of the input feature rather than just the whole vector. But for this fxi here, which is always a function of all of our x's, which means the x vector itself. So here in this expression, we got x0, which is 1 basically, and x1, x2, and up to xn. And we also have theta 0 up to theta n. So this is basically the raw hypothesis function, which uses all the input features or all the input parameters, as well as all, let's just denote theta or denote parameters by theta and denote the input features by x. So this function f here should include the input feature, the input features x, the input features which are the x's, or the elements of the input vector x, as well as the parameters, which are basically the elements of the vector theta, or the different thetas that we have within the vector theta itself, which are theta node and up to theta n. And the same thing goes with theta 2, or we can be more general and just say theta, let's pick a variable that we haven't used before, for example, theta v maybe, is equal to theta v minus alpha over m multiplied by the summation of I equals 1 up to m f of x vector I and also theta, which is the vector theta, minus yi, multiplied by xi, a particular example, and at the same time, it should have the same subscript, v, as theta v. So this is basically the general formula for gradient descent for a multivariable problem. One last note that we need to add here is we got to ask ourselves the question, what if the function is not linear in the parameters? What if the prediction is not based on a linear function, but rather a nonlinear function? So what are we going to do about that? Actually, the answer is quite simple, because, for example, if the function f happens to be of the format, for example, let's just say x and theta, where x is the vector and theta is a vector as well, happens to be like this. So let's just say theta node plus theta 1 x1 squared plus theta 2 x2 squared, for example, or x1 x2 maybe, plus theta 3 x3 squared plus. So you can find that our input variables here happen to be nonlinear functions, actually, which makes f itself a nonlinear function in the input features. You needn't worry about this, because simply what we're going to do is that we will consider that x1 squared in itself is a new parameter or a new input feature called, for example, z1. And let's just denote that by another color. And x1, x2 is just going to be z2. And x3 squared, we can just call that z3. So it turns out to be actually quite the same eventually. And we can just use the same linear methods that we used before. So this is some sort of treating the nonlinear function as a linear function. And the reason we can do that is because we are interested in having the parameters theta, the parameters theta node and theta 1 and theta 2 and theta 3. We need them to be linear factors. But for the input features, it doesn't actually matter if they are linear or not, because eventually we'll just get the overall picture or overall value and just consider that to be the linear factor that we need. So what's important is to have the parameters themselves as constant values. Whatever their factors might be, or the input features that happen to be multiplied by them, it doesn't really matter, and we can just treat it the same way. Except that the function f would have a different shape eventually. But still, we can apply the same rules. And the decision boundary here, instead of just being a linear function like this, it might look something like that, for example. Maybe a circle, for example, separating some area from another area. So we get an internal area here, for example, and some external area here. It doesn't really matter how this function f looks. What matters is we still can create a function that is able to predict the proper values for our problem. So to summarize, we now understand how linear regression works and the basic mathematics behind this machine learning concept. And next time we're going to work on an actual linear regression problem, and we're going to code our project using Python.